Thank you very much. And it's a pleasure to be here. I'm going to talk about arithmetic randomness today. So here is a picture. This spiral, what does it represent? Well, it represents the values of the Liouville function. And it looks pretty random. So the Liouville function is the function lambda over n is equal to -1 to the number of prime factors of n, counted with multiplicity. And there is a guiding heuristic in analytic number theory that the statistics of this Liouville function should be reasonably similar to those of a random sequence of +1s and -1s with 50-50 probability. And we have several examples of this phenomenon. So if you look at the partial sum of the Liouville function up to x, this we know is little o of x, and in fact this theorem is as deep as a prime number theorem. And if you are like a simple random walk, then you expect to have square root cancellation in such sums. But if you could prove this for the Liouville function, then you would prove the Riemann hypothesis. These are equivalent. So this is for long sums with one Liouville function, but you could look at correlations of the Liouville function with itself. And this is what Yoni already talked about this morning. It's a Chowla conjecture, but now we're going to look at the logarithmic Chowla conjecture. So my averages in this slide are going to be weighted with this 1 over n factor. And the logarithmic Chowla conjecture predicts that if I have any k distinct shifts, h1 up to hk, then this logarithmic average of the Liouville function should be little of 1 as x goes to infinity. And this conjecture is known for, in several cases. So for k is equal to 2, if you have two Liouville factors, then Tao proved that the logarithmic Chowla conjecture is true. And you can make his bound quantitative, but it's very, very weak. And there was later work, including Helfgott and Liouville, who gave a different proof. Instead of using entropy, they used ideas of expander graphs. And I refined their proof to obtain the following bound. So if you have two Liouville factors, then you can save a small part of a logarithm. So this is for k is equal to 2. And as Joni mentioned this morning, it is also known for k odd. So this is what he proved with Terry in 2017. But if k is even and larger than 2, we don't know the logarithmic Chowla conjecture.
So for k odd, what sort of bound?
Very weak bounds. So now I'm going to look at another instance of pseudo-randomness. I'm going to look at the Liouville function in short intervals, more precisely in almost short intervals. So here I have a long interval from x to 2x, and inside it I'm going to look at a typical window of size h. And for this there is the spectacular Mathématiques theorem from 10 years ago that says that you can take your window h as a function of x. If it tends to infinity with x, then we know that in almost all short intervals there will be cancellation. So for a typical window, if you look at the partial sums of Liouville, you have cancellation. And so this is very nice. And together with Tao, they showed that you can also add in some Fourier phase here, some linear phase. But importantly, you have to choose the same alpha for every little window. So if you fix your alpha, then on average, the Liouville function cannot correlate in short intervals with this linear phase. But the Fourier uniformity conjecture tells you something stronger, tells you that the Liouville function should really be Fourier uniform in almost all short intervals. So what this means is that for any short interval, if you choose the worst possible alpha, which can depend on the starting point of your interval, then you should still get cancellation in almost all intervals. And you can have a variant of this conjecture with a nil sequence instead of a linear phase, but today I will only focus on the linear case. So this is the Fourier uniformity conjecture, and it's a conjecture because we don't know it for every function h of x going to infinity. In fact, the smaller you want your function to be, the less we know about this question. So here is the Fourier uniformity conjecture again, and it's interesting in its own right, but it will also have some important consequences. And these are the logarithmic Chowla and logarithmic Sarnak conjectures. So I won't define the logarithmic Sarnak conjecture, but these two conjectures are equivalent, and they're also equivalent to a version of the Fourier uniformity conjecture. And in fact, if you want to prove either of them, and you will have to, it's enough if you can prove this bound for intervals that are of size log x to the epsilon for every epsilon. If you can prove that, then you will establish the logarithmic Chowla conjecture. And also, well, if you look at the Helfgott-Riemann approach for two-point correlations, so they use graph expanders, but if you could extend this to hypergraphs, which we don't know at all how to do, then you would also need some input of this form, but you would only need to establish this conjecture for h much larger, e to the log x to the 1/2 minus a little bit. So this is what we would like to prove. And now I'm going to tell you what is known about this conjecture. So the best known unconditional bound is that of Walsh, that says that the Fourier uniformity conjecture is true if you look at intervals of size x of log x to the 1/2 plus epsilon. You can be more precise in the epsilon as well. This improves earlier work by these authors. So you can see that this is very close to what we want for the second point here. And in a separate paper, he later showed that if you assume the generalized Riemann hypothesis, then you can shorten your interval quite a bit, and you can only, well, you can show that there is no correlations in almost short intervals for intervals of length log x to the psi of x, where psi is any function that you like that goes to infinity. So really quite short intervals, but still this is just a little bit worse than what we would like here. We want a function that goes to 0. Okay, and today I'm going to tell you about a new result that's not on archive yet. And this improves the unconditional bound of Walsh. So his exponent of 1/2, you can improve to 2/5. So let me tell you about the ideas going around in all of these proofs. And it's a little bit technical, so I will only talk about certain key ideas, and I will not go into all of the details. But roughly speaking, all the proofs have these 3 main steps. So it's a proof by contradiction. You assume that there exists some unknown frequencies alpha x, such that the Liouville function does correlate with these frequencies over many short intervals, so you have this bound. So this is what you start with, and then you would like to derive a contradiction. But the difficulty is that you don't know anything about these alpha x to start with. And what you are going to do is you are first going to apply the Tyron-Kubelius inequality, and this will tell you that these alpha x, they are not completely unknown. They have some relations between them, but the relations are only between certain pairs of frequencies. And then you have to do some complicated combinatorial analysis to leverage these local relations and hope to get a global formula for what alpha x is. And then with some simple Taylor expansion, you are reduced to the Mathématiques theorem, which is basically the case where alpha x is, for example, a constant or a known function of x. So let me tell you about the first step, which is the application of the Tyron-Kubelius inequality. So here is a rough statement of it. So you have a one bounded function f, which is completely arbitrary, and that's defined on an interval of length h. And what the Turing-Kubilius inequality tells you is that the average of f over this interval, well, it's very close to the average of f, where you only look at the numbers n in your interval that are divisible by p. And this is true for many primes p in a certain range. And here, well, the lower bound for p is h to some constant, and this constant depends on how good you want your approximation to be. So this is the Turing-Kubilius inequality. And then we use another fact that just follows from Parseval. So if you look at an average like this, a correlation of any function, one bounded function with a linear phase, and if this is very large as possible, up to a constant, then it turns out that there is essentially only a bounded number of possibilities for your alpha. So S is the set of frequencies alpha. Okay, so if you want the Lebesgue measure of the set of alphas for which this holds is bounded by big O of 1 over h. So now let's use this to obtain our local relations. So by Turing-Kubilius, there exists some scale p, which is a small power of h, for which there are many pairs x and q, where x is a number in this range, and q is a small prime number of size roughly p, such that the average of lambda of n with my linear phase is close to that where I only look at the numbers divisible by q. And now I'm going to use the multiplicative property of the Liouville function, and lambda of n I write as lambda of m times q, and then by multiplicativity I get this expression, and this is an average. So I've changed variables, and now this is an average of a smaller scale where I have a smaller interval from going from x over q to roughly x over q plus h over p.
I think it's less than Turing-Kubilius, right? I mean, it's basically a weak form of the large field.
Well, we can talk about this later. So questions are for later. Now, if you have two intervals at this scale x, and well, it's possible that there will be primes p and q such that the two smaller intervals, they are essentially the same. So they overlap for most of it. So this happens if x over q minus y over p is smaller than a small constant times h over p. And then the small intervals are basically the same. And what this means is that if you already know that this original sum in red is close to this sum, and this one is close to that one, then very often you are going to be able to deduce that actually those frequencies, alpha xq and alpha yp, are the same, up to a very small error. So this is because we know that for a sum of this type, so a sum like here, there is essentially a bounded number of frequencies that can make it large. And so if you have many pairs xq, you will have some that correspond to frequencies that must be roughly equal. So the conclusion of this Turing-Kubilius business is that if you have this correlation estimate, then for some h-separated set of points, so A is my set of points, so A is my set of x's above, there will be almost as many as possible quadruples x, y, p, q, satisfying these two bounds. So this bound is saying that the smaller intervals, they overlap for most of it. And this bound is saying that the associated frequencies at x and y, they are related, and this is a precise relation. And here, curly p is the set of primes in p to 2p. So this is the first step. That's common to all the proofs. And then there is the combinatorial analysis, which depends, well, well, it has been improved over time. And this is the heart of the proof. Now I'm going to make a useful definition. A configuration with concentration delta is going to be a pair where A is a subset of y up to y, a set of integers. So here I have changed variables to make my life simpler. And then the alpha x's are just frequencies associated to every point of A. And having concentration delta will mean that there are at least delta times the size of A times p squared, quadruples like this, that satisfy those two inequalities. So here observe that if you choose x, p, and q arbitrarily, then y will be uniquely determined by this relation. So the maximal number of quadruples is at most the possibilities for x, which is a, and then p and q, which is p squared.
What's the relation between the size of the p and q and capital P?
So capital P is the set of primes between p and 2p. Yeah. Now I'm going to give you an example. If your frequencies are always given by this formula, alpha x is t over x, then you can have many relations. So these configurations, they exist. So you cannot directly get a contradiction from studying them because you have examples of those. And this is an example where if you look at any quadruple satisfying this bound, and if you look on the frequency side, and if you replace alpha x by t over x and alpha y by t over y, then you will get that this is small. And so at least if t is not too large. And so this creates a whole family of examples of configurations with large concentration. And the goal will be to show that actually this example and maybe some related variants are the only ones that are possible. And now I will show you why this is useful. Because if you have a formula for what the frequencies are, you can apply the Mathématiques irreducible theorem. So here is the simplest example. If you know that your frequencies are t over x, then you have a correlation like this. So it's easier because you have a formula for the frequencies, and now you can do some simple Taylor expansion, and E of n t over x is essentially n to the 2 pi I t. Maybe you have to reduce the interval length a little bit, but you can do that. And now this is a multiplicative function. What this means is that you can just apply the Mathématiques irreducible theorem, and you will see that such an estimate is impossible. So I've told you about steps 1 and 3 of the proof. So the reduction to Mathématiques irreducible theorem is here. And then how to obtain the local relations I explained to you. But the heart of the proof is the combinatorial analysis. And now I want to tell you a little bit about what Walsh did and how I improved on it. But I cannot go into too many details because I only have 15 more minutes. So I will give you a very, very rough idea of what goes into it and what are the difficulties. So if you look at my local relations, you see that every frequency alpha x on average is related to p squared other frequencies. Because you have, if you choose x, then you often have like a constant times p squared possible pairs p and q, for which it's related to another frequency alpha y. But now we want to relate all frequencies together. And what this means is that you have to do some sort of iterative argument that maybe starts at some point x, and then you have to expound to reach all the frequencies. And this means that the number of steps you will need to do in this iterative argument will be log y over log p, because y is the size of your set A, roughly speaking, and then, well, this is log p squared, is a constant times log p. And I will not tell you what these iterations are, because they are a little bit complicated, but they are called lifts. And I want to tell you how we can how we can make sure that we can have so many lifts, because this is quite large. So a main difficulty is that if in every iteration you lose a constant factor, and since you have these many steps, the total loss will be of size e to the log y over log p. But you can only afford to lose a factor that's basically p to a small constant. And so if your lifts always lose a constant factor, which already seems quite efficient, but it's not efficient enough if you want to get down to p, which is smaller than e to the log x to the 1/2. So you have to design a combinatorial procedure that doesn't lose this constant factor at every step. Otherwise, you can only get this bound, which is the Walsh's bound, the first one. I'm going to tell you about how Walsh did to go past this barrier, assuming GRH. And roughly speaking, Walsh proved this key structure theorem. So Walsh proved that if you have a configuration where the side of the set is a constant proportion of everything, and the concentration is very large, then one of two things happen. Either your configuration has a lift, and there is almost no loss, so we are very happy, and we can iterate this many times if there is almost no loss, or there is a subset of A prime, which is not too small. And if you look at the configuration that just consists of restricting to this subset, then the concentration is still quite large. So it's at least the original concentration, and then you get this factor, which is the ratio of the two sizes, to some constant which is less than 1, importantly. But you could prove it with any constant here, that's between 0 and 1. And now he used another fact, that if you assume the Riemann hypothesis, and if p is at least some power of log, then any configuration A where the density, so the size of A divided by y, is at least p to minus c for some small constant c, any configuration like that must have concentration which is quite small. So if it's bounded by the density. So if the density gets small, then the concentration gets small as well. So this is a picture. So the blue line represents, okay, first the axis. So this axis represents the density. Actually, it's like log of 1 over the density, because it will make the picture more readable if I do a logarithmic scale. So the density is on this axis, and the concentration is on the other axis. So I'll take log of 1 over the concentration. And this lemma that comes from the Riemann hypothesis tells you that there do not exist any configurations in this range. So this is a line of slope 1. And you can never have a small density. So the farther you go there, the sparser your set A is. You can never have a small density with a very large concentration. And we start with a configuration that's about here. So very large concentration, very large density. And then we apply this key structure theorem repeatedly. And then we see what happens. So because of this exponent 1/2, anytime you are not in the good case, so you are in the second case, you can pass to another configuration, and your step will look like this. So you lose a little bit in density and a little bit in concentration, but importantly, the slope here is bounded by 1/2. And so if you repeat this operation again and again and again, you will soon be close to entering the forbidden zone. But of course, the Riemann hypothesis tells you that you can't go there. So after a bounded number of steps, you will never have the second case anymore. And so you can lift again and again, and then this provides you with the global formula. I'm going to tell you what you can do if you don't assume the Riemann hypothesis. And it turns out you can use some ideas from this proof to prove the following theorem. So this is this is the key ingredient in my new work, is that it's a relative structure theorem. So I will explain what this means. But basically, it also works when the size of A is really quite small compared to Y. Whereas for Walsh's theorem, you really needed that A is very large. And also you have this loss here. Okay, so let me tell you about this structure theorem. So if you have a configuration with very large concentration, and again, one thing that can happen is that you have a lift with almost no loss. So this is the good case. But we improve on the second case. And the second case is where you have a subset that has at least halved in size, but is also not too small. But now the concentration has, well, it's much better than before. So what you have lost in the concentration, you pass from delta to delta minus a little bit. And this little bit is 1 over log p to the 1 minus little of 1. So we have this theorem, and then we want to use something that replaces the Riemann hypothesis, and using some Vinogradov-Korbov differential polynomial techniques, we can prove the following. So for any theta, if p is x of log y to the theta, any configuration with very large concentration cannot be too sparse, so the density must be at least e to the log y to this expression, 1 minus 3 theta over 2. So I'm going to draw the picture again. So this is what Riemann hypothesis tells you, and this is what the Vinogradov-Korbov assumption tells you. So here we are really looking only at very large concentrations. So this lemma is only useful when you are looking at configurations with very large concentrations. So this means that the region doesn't go very far up. It's bounded in height. And also, it only starts to be non-trivial when the density you want, when it becomes really small. Okay. So this is a region that's forbidden. So you can never have a configuration with these parameters. And now we also have our relative structure theorem. And so here, what's important is that the concentration goes from delta to delta minus 1 over log p to the 1 minus little of 1. So this means that we can perform roughly log p iterations of this lemma, and still the concentration will only halve. So let's iterate this lemma. And now it's much less lossy, and so the slope here is almost 0. And so maybe we have to iterate the relative structure theorem about log p times, so a lot more times, not just a bounded number of times. But since it's almost not lossy, we will arrive in this forbidden region. But this can't happen. And so when you are here, you know that you are going to be in the first case when you have a lift, and then you can keep iterating those lifts to prove the global relation. So I'm going to finish this talk by telling you why the exponent 2/5 comes up. So this is just the exponent such that 1 minus 3 theta over 2 is equal to theta. So this is why you get 2/5, and these 3/2 comes from the Vinogradov-Korbov techniques. And you could improve this exponent that I gave you if you could solve the following problem, but I wasn't able to do that, but maybe you can. So choose an exponent that's smaller than 2/5, for example this one, and define p to be of this size, e to the log y to the theta. And again, curly p is a set of primes in that interval. And now I'm only going to look at the first conditions out of the two conditions that define the local relation. So this is a condition of this type. And here I'm asking that I'm asking you to prove the following estimate. So if the number of quadruples satisfying this estimate is at least as large as the trivial bound up to a constant, then you have to prove that this is only possible if A is not too sparse, and the sparsity that I need is P to a small constant. So if you can prove this, and also prove some modular variant, then you will improve on my result. And another open problem, which is supposed to be simpler, because if you can solve problem 1, then you can solve problem 2, except that the statement of problem 1 is a little bit more involved. And the only way I know how to solve this for theta bigger than 2/5 is to prove problem 1. So we fix theta p and curly p as before. And now we assume that we have not just one set A, but a whole partition A1 up to AL of this integer interval, where every set is of size y over L. And now we assume that, well, if you sum these quantities for every I, then you get something that's almost a trivial bound. And I'm asking you to prove that L is bounded by this small power of P. So, so this is exactly saying that each AI is at least a small power of P times Y. Thank you very much.
Thank you very much. Question?
Could you replace primes by products of 2 primes? Wouldn't it be a bit easier?
So here, in these problems, it's not very important that they are primes. So you could also look at the set of all integers in this range, and I don't know how to prove this.
I believe use of Vinogradov-Korolev would not be necessary if you did stuff like that.
So what is the question?
Well, just if you had a more general set that you were dividing out by, could you avoid using Vinogradov-Korolev and get better results?
No, I tried many variants, and this is as far as I went.
Of course you did.
Can you go back to your picture and maybe explain about what Walsh was doing? For example, he has 2 results, one where he assumes right, one he just used Vinogradov-Korolev. What is his picture look like?
So I don't think Walsh relies on Vinogradov-Korolev. So Walsh has one conditional result that's conditional on GRH, and it's this result. And then his
Or exponential sums over time.
Yeah, I'm not sure he relies on anything. He just used some very trivial bound in the case of e to the log x in 1/2. It's a much simpler proof.
I mean, he has 2 papers. In the first 2, which are extremely elegant, he uses the little number theory.
Yes, exactly.
And the third one, he does do exponential sums, but I
Yeah.
don't have a good sense of how essential it is there.
So he doesn't use exponential sums in the first 2 papers, and he used GRH in the last one.
He gives some sketch.
So this is the last question. Thank you again.